Today I'm going to start with the difference between a 6S and a 36S. 36S is, and there's also a 46S. 46S ends up with 4 potential sensors, or it's really not a solid, it's not an electromechanical meter, so if it was an electromechanical meter, there'd end up being 4 potential coils, and then this idea of the Z coil still would be in a 46S. So I don't have any diagrams of 46S in any of my books, but if you're interested in seeing the 46S, I think GE is the one who makes the 46S. My experience with the 36S comes from a ABB meter that was a 36S. So it's a direct replacement. The 36S is for a 6S. The 6S meter often is described as a 2.5 element meter that you might see somebody who has written to, oh, that's the wrong pen. Let's get the right pen here. Okay, as a 2.5 element meter. In the 6S, there are two potential coils. First potential coil is connected from, and I'll zoom in here so you can see this. I can write around it. So first potential coil is connected from the far left-hand terminal. In the center terminals, the 7 terminals go through the center of the meter socket, and the meter is connected from the far left-hand terminal, and its non-polarity side goes to a neutral connection that is the far right-hand side, and so that's the first potential coil. Second potential coil starts on the next terminal in, and so far left, second far left. This one also makes a connection through the potential coil to a neutral. So a neutral here and a neutral here in the 6S. 2 current coils that are what we call a regular or normal style current coil. The blue current coil has a relationship to this first potential coil. And so it's a full current coil. And and I'll show you a diagram in a second where and how these currents are connected inside of a service. And so this meter, the Form 6S, and since there's, in case anybody else joins, they can see where we're at. This is a Form 6S meter. That, like I say, the first current coil, that's the blue one here, has a relationship to this potential coil. The second current coil, which is considered to be the Z coil, this is the one that a lot of folks want to call a half an element. It has similar theory to what a 2S meter would be. 2S meter has one current coil like this blue one that goes through, and then a second current coil that is physically wound backwards compared to the blue current coil. That's what you'd see in a 2S or a 4S type meter. Also in a 15S and 8S meter. That 2S meter theory is in all of those different meters. That a current coil, and then a current coil that is wound backwards against it, and they both share one potential coil. So that's the 2S meter theory. The difference between this and the 2S meter theory is that in the 2S, the currents that flow in these two are 180 degrees out of phase with each other. And that would be in the 2S meter theory. In the 6S meter theory, we end up with, instead of having 180 degrees between the blue current and what's happening in the black current coil, they're only 120 degrees out of phase. And so you get a little different effect from this phase relationship in this meter we call a 6S or 2.5 element meter with that Z coil with 120 degrees between these two currents as opposed to 180 degrees that would be in the 2S. So I'm going to leave the 180 out of this just so you can see that. The other thing that happens in the 2S is that these end up being half current coils, that the blue current and the black current that you would see inside of a 2S meter are half current coils, and how they're described as half current coils sometimes becomes very confusing to folks. But one of the things that goes along with all of the current coils in our meters that and this is for electromechanical meters, that all electromechanical meter current coils are 60 ampere turn coils. All current coils in all of our electromechanical meters are 60 ampere turn current coils. Now, how that works in a 2S meter, where a 2S meter has, we'll say, a test amp of 30. It has class amps that equal 200. That with the 60 ampere turn, what ends up happening is in this current coil, I have one blue current and one black current that would be in a 2S meter that would put one turn for the first, or the blue would give me 30 through the current coil because there's one turn from it, and then the black one would have a second turn, and so 2 times, or 30 times 2, one for what would be a blue current coil inside of a 2S, a black current coil inside of a 2S, 30 times 2 would give us 60 amps inside the meter current coil. Now, if you take the same idea of the 60 ampere turns, and if you still have electromechanical meters, it's something that you can see very easily. That if you go find a form, this is, I'll go right here, form 12S meter. That's a 2-element meter. That's also a TA30 and a class 200. This meter would be a 2-element meter. The 2 elements in this meter are elements in this meter are what would be seen as 2 form 1S meters. Now, not connected like 2 form 1S meters would be if I had 2 form 1S meters I could put in the socket at the same time. What happens is I end up taking the theory and everything that goes along with the 1S meter and combining it into 2 elements where each element would be the exact same theory as a single 1S meter. So back to the idea of this test amp idea. If you can find both of these meters, this would be the 2S, and then the 12S with both of them have the same test amps, both are class 200 meters. In the 2S, I end up with one turn from my blue coil and one turn from the black coil, which gives me 30 times 2 or 60 amps. For the 12S, when I see it, what I end up with is in each element, each current coil in that meter has 2 turns in it, just like this one does. This one has 2 turns. Okay, when you look at the form 12S and see the test amps adds 30, there's still 2 turns here, but in this meter, the 12S, in each one of the elements, you'll see 2 turns in each current coil, but in this meter, those 2 turns are coming from one current path. There's not 2 different current paths in there that add up to 2. In the 12S, in both current coils, you'll see 2 turns from each current coil making up the 60 amps. So up here, I get half the torque from what would be one side of my 2S, half the torque from the other side of my 2S current coils, where here I still get half the torque from each turn, but in this one I have just one current path, or the blue would go through once, go through a second time, and I'd get 2 turns at 30 amps apiece. So if you have a 2S that's electromechanical, a 12S that's electromechanical with 30 test amps each, class 200 meters, this is a 2-element meter. Doesn't matter the voltage on this. What we're looking at is the current coil. As you look at the current coil, in this meter there'll be 2 turns inside the current coil. This one will also have 2 turns, but it'll come from 2 separate current paths in the meter. So that's something that is the 2S meter theory. In this one, as I look at this one, I would have 1 turn from each one of these, okay, and I'd end up with 2 turns inside. Well, this is a 6S, so I can't do that, because with a 6S I end up with 24 turns. So the theory that's just behind this one is very similar, where this one's wound backwards, but at the same time these don't end up being half current coils. I get full torque from this black current coil as it's wound backwards compared to the blue and this potential coil. As I follow this black current around, it comes around and it's also wound backwards compared to this red current path or current coil. It's also wound backwards, where this red current path and this potential coil have a relationship that I'll show you in a minute with the vector diagram. And then this black, which was already measured here by this phase relationship with this potential coil, will be measured a second time against this potential coil, and then off to the load, or back to the CT, because this is a instrument rated meter. So CT coming in, current coming in, goes through this current coil, goes through this one, both of them wound backwards compared to the 2, what would be seen as the 2 that would match as far as the current in this one and the polarity voltage on a potential coil are coming from the same phase. So if this was marked as, let's get a color here that's kind of close to that. This was IA current here, then the polarity voltage on this potential coil would be voltage A, would be the polarity, and then the non-polarity side is to neutral. So the potential coil here has A to neutral voltage across it. Over here, I'm going to go to a red pen. This would have IC current in it. Oh, I say IC and write IA. That's sneaky. That's sneaky of me. But so I put IC here. That's the current. This IC CT is feeding this current, and then the polarity side of this potential coil is going to have VC, voltage C, and then the opposite side of this potential coil is neutral. So it has voltage C to neutral across it, with IC current having the first relationship with it, and then what would be minus IB here, minus IB here, and minus IB here. Let's see, I'll write this right here. And so that's how this would be. So minus IB has a relationship to this potential coil, minus IB has a relationship to this potential coil. So as we see those, I'm going to go over to how the vector diagram would look for this meter. That this is the system vector diagram. That this is what the transformer is putting out. That there's 120 volts, and there's 3 different 120 volt voltages. And so as I would zoom in on this one from the transformer bank, let's just skip up a little bit here. As I look at the voltages that are available here between what's the common conductor for this transformer bank itself, that is, this common conductor is our neutral, that is the center point of our Y vector diagram here. That center point is that Y point there. That between the green conductor and the blue conductor, I have 120 volts, which is being represented by this vector that starts from the neutral point, ends up pointing out towards where the 0 degree line would be on a vector diagram graph. That the second voltage, which is voltage B to neutral, as I look at it, that's this voltage from green over to black, and so there's 120 volts there also. So 120 volts phase to neutral on B phase, and on C phase that becomes the green to the red, which is this 120 volts. Between the phases we have what is 208 volts, and in actuality the math makes this into 207.84 volts. Calling it 208 is fine, but in some of the truths that have to go with this and the vector math that goes with this, if I take these 220 volt legs and add them, well, let's see, that's a subtraction because it would be up here, I would end up with 207.84 volts from phase to phase. Same on all 3 of those. Don't let that confuse you. 122.08 is great, but in actuality the vector math would prove that at 207.84. And so that's what these phase-to-phase voltages become, between blue and red, between blue and black, and then black and red. So that's what the 208s would be. So this is your system vector, and from the system vector we have 3 CTs in our system. We're going to meter this with what's called the 2.5 element meter, the Z coil meter. All those different things come into play here as people describe these. That as this is wired for 3 CTs measuring the current in each one of the energized phases, then as I see the CTs coming in to here, my blue CT polarity comes into the top, and then non-polarity would go out the bottom. The black CT polarity comes in the top, non-polarity comes out of the bottom. When I say polarity, I mean X1 from the CT. For red, it comes in on polarity, or X1 on the top, goes through the current coil, and then returns back to the source there. And so as I see the system vector and compare it to what the meter vector is, and I'll zoom in on these two, as I see the system vector and the meter vector, in the system vector I have 3 voltages and 3 currents. In the meter vector I have 3 currents still, A, B, and C, but this meter only uses the 36 or the 6S, both of them are the same, only has 2 potential coils in it, 2 potential coils here, 2 potential coils here, and so both the 36 and the 6S meter are the Z-type coil meter. And so as I look at how this is put together, keep it in mind that this current that comes in here is wound physically backwards compared to the blue one that's going through in phase with its voltage. That as I look at vectors here, this is the system vector, this is what the customer's getting, that at unity power factor, a current that would be flowing in this system would be right in phase with that voltage. That's this first one here. That's what would be in this current coil, and IA would be in this current coil, and voltage A to neutral would be across this potential coil. As we look at the other element number 2, and look at the phase relationships there, I have now voltage C to neutral across my second potential coil. I said that when I was explaining this, and so C to neutral voltage across the second potential coil, and then IC current, which would be this current flowing in the system, in phase with the voltage of the system that's C to neutral. And so this current would be this current, C to neutral voltage would be this voltage, and that would be the two voltage and current pairs that have the relationship in each element by A phase voltage, A phase current, C phase voltage, C phase current, and now B phase current, which in the system now is this current right here. This is it in the system, sitting out like this. This would be IB current. As that current comes and is wound physically backwards, it takes this current that would be here, winding it backwards, it ends up being 180 degrees out of phase from where it is in the system. This is the system vector. This would be the system vector on this diagram, but since this is wound backwards, this one is flipped over, and now as current flows in this one, minus IB would have a relationship with this voltage. It would also come around, have a second relationship with this voltage, that's it right here, coming through here, and then back to the CT. And so as a Z-coil meter is put together, I'm going to take this one back out because that's the system, that's the meter. As the meter sees it this way, and how this will work correctly, that when we solve for watts in a circuit, if I was to say I have 120 volts, again, just get a little different color pen here, say 120 volts here, 120 volts here, and then 5 amps, and we'll say 5 amps here, and then 5 amps here. As I have those relationships at 120 volts and 5 amps for this first relationship, which is the blue current and the potential coil, blue to green potential coil there, as I would solve for the watts for that element, as I start to solve for watts of the element, I would take the voltage times the current multiplied by the cosine of the angle between them, and that would give me the watts. So as I have that, 120 volts times 5 amps here says that that would be the volts times the amps, and then multiply by the cosine of 0 degrees, because these two are right in phase. Cosine of 0 degrees is a 1, so I'd have 120 times 5 times 1, and that would say that that is equal to 600 watts. So that would be how I would approach each one of these current and voltage relationships. As I look at this one now, I'm just going to change the pens to red as I do this one. Same formula, I would take 120 volts times 5 amps times now the cosine is 0 degrees again, because these two are in phase. Cosine of 0 degrees is again a 1, and so I'd end up with 600 watts from those two. So 120 volts at 5 amps, 120 volts at 5 amps gives me 600 watts and 600 watts. Now as I look at this 120 volts and that 5 amps, and now let's get a pen here, looking at the phase relationship between this voltage and that current, I'm going to give this to you at minus 60 degrees. That as I look at this 5 amps, this 120 volts, I'm going to still have 120 volts on my potential coil times 5 amps times now the cosine of minus 60, which is 0.5. If you have a calculator nearby, you can try that. So 120 times 5 times 0.5 gives me 300 watts from this relationship, this current, this voltage, and that 60 degree minus, which is a 0.5. And then from there, as I look at the other element, this now is 60 degrees here. So I look at that one, I would have 120 on my potential coil. I would have times 5 amps in the current times the cosine of 60 degrees, which again is a 0.5. I would get 300 watts. And so in the first one I had 600. In the second one I had 600, and between the two on the black current with each of those other voltages, as I take 300 plus 300, I get a total of 600 there. And so I'm getting the same amount of torque from each one of the currents and the voltage that they're related to. So that's how a 6S meter would see these loads. So these are just arbitrary numbers that I came up with, but I just wanted to show you that as the first current and voltage work together, I get 600 watts from there. The second current and voltage work together, I get 600 watts there. As IB, which is the minus IB, has a relationship to this voltage, it would be this one here, 120 volts still, times the 5 amps that's IB current, times the cosine of minus 60, which is a 0.5, gives me 300 watts there. And then for this 60 degrees, this voltage and minus IB a second time, 120 times 5 times 0.5 gives me 300, a total of 600 watts between the two. And again, this 600 would equal the 600s that are from the ones that sit right in phase. So that's how the 6S measures loads. Again, as I come out and show you the system vector, the meter vector, the phase relationships that are in here. Now, as you see this, the 6S meter is the instrument rated meter that is used on 4-wire Y. The reason we use 6S meters is in the day when we had lots of electromechanical meters that they were buying, the utilities, putting in a meter with 3 potential coils, as opposed where a 9S would have 3 potential coils, as opposed to 2 potential coils. The what my boss used to tell me, that it was $100 less for a 6S compared to a 9S. So where I was a meterman in Utah as an apprentice and for a journeyman for many 4-wire Y installations, we very seldom put in a 9S meter. We were always putting in 6S meters. So that's the theory behind the 6S, as opposed to how we would do it with the 9S. That's something that we're not going to cover today, but that's how the 6S would see that. As we look at the wiring of the meter socket and how it would be wired, like I say, A phase, B phase, and C phase currents, I've already showed those. As I look at the voltages, A phase voltage would be here, B phase voltage would be in the second, C phase voltage would be in the second position here. So A and C, that's the voltages across my 2 potential coils. A to neutral and C to neutral. And in the 6S, there were two individual potential coils. When I say individual, that from blue to green, from outside to outside, there was no connection from that first potential coil from outside to outside to the next potential coil in, or the C to neutral potential coil. And so you had to put both of these right-hand side terminals, both of them had to have neutral connected to them. And so that's how the 6S would be wired. So A phase current, B phase current, C phase current, all those are the polarity currents. A phase current, B phase current, C phase current would be the non-polarities. A voltage to neutral is the first potential coil. C voltage to neutral is the second potential coil. And so that's how that would be wired. Now taking that 6S, I'm going to just go up here and we'll look at it one more time. This is the 6S. So blue, polarity, green or neutral non-polarity, that is the first potential coil. C to non-polarity neutral, so C to neutral across that one. And there's no physical connection between these 2 points, and so there's 2 separate potential coils. Back in the day when we used to put var hour metering in, this was our choice for a var hour meter because it had 2 separate potential coils, where a 9S meter has 3 potential coils but all of them share a common point. A 10S has 3 individual potential coils, so outside to outside for a 10S, and then the next one inside to inside, and then inside to inside. There'd be 3 separate potential coils in a 10S. A 9S is not that way, so a 10S and a 9S are both 3-element meters, but the 9S meter, all 3 potential coils are tied to 1 point. The 6S was used by us to put in var hour metering, where we would put in a phase shifting transformer, and with the phase shift transformer I could shift the voltages of the system and make it so I could measure VARs on a 6S. And so that's something that, again, as an apprentice and as a journeyman, this would be two 6S meters, one for watts, one's for VARs, and the VARs would have a phase shifting transformer that would allow me to measure VARs on the same style of meter. Now, comparing that 6S to what the 36S is, and I'll just label this because the rest of it's up above. This is the 36S meter. With the 36S meters, the current coils are exactly the same. A phase from top to bottom, B phase becoming minus IB as it goes through what's considered to be the Z coil, and then C phase being on the right hand side. And so the current coils are exactly the same. I'll come out a little bit here so we can kind of see them side by side. So as I look at the 36S compared to the 6S, current coils are exactly the same. So you can kind of just compare them as you see them side by side. As far as the potential coils are still, in this one, I'd have A to neutral voltage on the first potential coil. On the second potential, let me zoom in, that'll be easier to see. Okay, so on the first potential coil, in the 6S, it had A to neutral voltage. On the 6S, the next potential coil, or the second potential coil, had C to neutral. Where in the 36S, because the 36S is an auto ranging meter, 120 to 480, since it's an auto ranging meter, one of the requirements of an auto ranging meter is that all the potential coils in the meter, there's 2 potential coils here, have to have a common tie between them. That this potential coil, which in the 6S ended up at the same place exactly from outside to outside. That one is no different in the 6 or the 36. In the 36, where this potential coil would come to here, and then in the 6S it'd come back and connect to here, and then I'd put neutral on both of those two. And then I had two individual potential coils. Because this is an auto-ranging meter, like I said, one of the requirements of an auto-ranging meter is that all the potential coils in the meter are connected to one point. I end up with A to neutral voltage, C to neutral voltage, just like the 36S, like the 6S, but as they're tied, you end up being only one point that you have to put a neutral connection on inside of your meter socket. Now, if you went out and had a 6S meter in this socket and replaced it with a 36S meter, would there be a problem with leaving both of these tied down to neutral? There won't be any problem there because KYZ still sits in the same center point. And so if you took out a 6S that has two individual or separate potential coils and took this 36X and plugged it in, you really don't have to worry about having that neutral there because it's really a terminal in the meter that nothing goes to. You can see that in this diagram, that this terminal in the meter, there's nothing connected to it. KYZ is in the same point it was in the 6S, KYZ here, and then that position there. Now, if you're going to install a new 36S, you don't have to put this wire in. There's no need to. You need this one. You need the one that goes to the outside terminal inside of the meter socket that both these potential coils are connecting to it. You don't have to put this one in inside of a new socket if you were to put in a 36. It's just unnecessary to have both of them there. Maybe companies still do that. That's one of the things that that I talked about when I was talking about the 5, 35, and 45, that a 5S on 3-wire delta will jumper the two center bottom terminals together. But when I put a 35 or a 45S in that same installation, I really don't need to jumper those two bottom center together. I only need to put a B phase to the bottom right center one. So it's, again, by practice, people might still be doing it that way, but it's not necessary. So as we see the two different meters, currents are exactly the same. I'm going to zoom back out here. Currents are exactly the same. Current paths are very much exactly the same. And then potential coils differ in, both these potential coils are connected to here, where the 6S has two individual neutral points on it. So, any questions on either one of those? I know that when I was a meterman in Salt Lake, that we would put a 6S meter in, or we put lots of 6A meters into A-base meters. We had lots of A-base meters. We started getting socket style meters. I'd been a journeyman for about 5 years when we started getting, well, probably not quite then, about then. About 5 years when we started getting socket style instrument rated meters for 3-phase. Up until then, most of them were A-base meters. As we had the A-base meters or the 6S socket style meter that we put in on a 4-wire WYE system, we would, or many of us would, take and bring this voltage to the test switch. So we'd pull in all 4 voltages, all the current wires we needed. We pull those all in. We would have a voltage sitting here that didn't go anywhere with the 6S in case someday in the future we wanted to replace a 6S with a 9S meter. And so as we would do that, this voltage would just sit here unused in the 6S, and then if we took a 6S out and replaced it with a 9S, this voltage, C-phase voltage, would have to move over one. It had to move over to this position here, and then the black voltage, or B-phase voltage, will end up where that red one is. I'll kind of bring that in here closer now so you can see what. So we were going to change this from a 6 to a 9. Again, we would pull that wire in. It would just sit here. Oh, excuse me. It would just sit here unused, and then I believe that that's what I work at Seattle City Light full time, and we have a couple of 6S meters that we're going to change out as part of our AMI program. And as we do that, we're going to hopefully find with those that this B-phase voltage is sitting at the test switch. So as B-phase voltage is sitting at the test switch, then the process will be, the currents will stay exactly the same. Like I say, the 6, 36, and 9 now, currents are exactly the same in all 3 of those. It's 6, 36, and 9S. A, B, and C current as they're laid out here exactly the same. If I was going to put this in as a 9S meter, this will have to come over to here now. And so instead of going to the second position and it goes over to the third position, most all of us are familiar with how the 9S is wired. And then I'd bring the black voltage up and it would go to there. And so blue, black, and red. Again, if these two are sitting like this, with the 9S, potential coil from outside to outside, from black to outside, from red to outside. And so in the 9S, all 3 of these potential coils would be connected to this point. This one's left in place. Not going to bother anything, but you need to make sure that if you're taking this out and replacing it with the 9S, that you rewire this voltage to here and put the B-phase voltage there. This can, if I do this wrong, I can create some billing errors that can be very substantial. So make sure if you do any exchanges from a 6 to a 9 that you get it right, as far as getting those in there right. I don't know, I haven't visited either. I don't think from our record at City Light there's only a couple of these that are still 6S's that we have. As we do them, hopefully, like I say, we don't have to pull in all new wire, that we can just go from the top of the test switch in. If by chance, and again I don't have complete record of what's going on, but if they were on like a primary metering setup where there's only 2 PTs that are being used, then they wouldn't be able to be converted to a 9. They'd still have to stay as a 36S. So that's something that will still be determined, by our us as we do our meter change out. So any questions on that part of it? So as we see this meter socket like this being wired as it sits here now, a second issue that has shown itself, that's here, that I'll start to talk about a little bit because we have a few minutes left. But this is now a Form 9S meter. This vector diagram is exactly the same as far as how the service is connected. This is the transformer vector diagram. These are the currents that would flow in each one of the CTs and in the service wires feeding the customer. Neutral conductor voltages are all exactly the same as what it was for the 6S. Now this is one that was brought to my attention just recently. I had done this math before, but it's not one that I've done since then. But just recently, this was a question that came to me, that a 9S socket, and this 9S socket was wired, I'm going to zoom in here, where the neutral was connected to those 2 points. So here and here the neutral was connected with A, B, and C voltage here, and then neutral was connected to these 2 points. As neutral is connected to those 2 points, like I said, in a Form 9, I don't need to have it connected here because each one of these potential coils in the meter go blue to green, black to green, and red to green, as we look at that on here. As we go, A phase or blue goes to green, black goes to green, and red goes to green. And so every one of these potential coils have a common tie to this point right here. So if I have neutral connected here where it says KY, if this was Z and I had neutral connected there, that could be an issue. But on the one that was shared with me, there was no KYZ pulses. It just had A, B, C, and then 2 neutral points in the way the meter was wired. And so I'm going to come back out so you can see this. So that's how the socket's wired. This is how the 9S meter that would be plugged into there would work correctly, even though both of these have neutral on them. But what happened on the one that was in question, that instead of having a 9S meter plugged into this socket, mistakenly a 6S meter was plugged into there. And so the 9S, again, with those two like that, wouldn't have an issue. With the 6S, it makes it so both potential coils that are in the 6S, as I plug them into here and I see those 2 neutral points, that as I plug this in there and not have A and C voltage in my first 2 positions, with this one I'd have A and B in my first 2 positions. The C phase voltage would go unmetered. Okay, that, like I said, this is something that I'm just going to kind of give you a warm-up on. If you want to try to think about it yourself during the week, you can. This is what the metering ends up being in the end, that the currents stay exactly the same, that A to neutral voltage is still where it belongs, but instead of having C to neutral voltage like the 6 would want up here, it has B to neutral voltage. So if you want to kind of pursue that, you can kind of think your way towards something like this, that what we'll discover, let's come back to fit here, what we'll discover on this one, that with this meter plugged into this socket wired like this, that this vector diagram will give us the proof that this meter would be stopped. and it's something that that's what the question was. How would you see the meter, Brad? And I just said, well, from what I see here, it ends up being stopped. So that's the what's that called when somebody tells you the end of the story? Spoiler alert. That's the spoiler alert on this one, that when we're done with this next week, that this vector diagram here, instead of being this vector diagram, is going to make it so the meter plugged into there, even though there's current flowing, even though there's plenty of load out here, this vector diagram proves a stop meter, as opposed to what it should have been with this one, which would have metered it correctly. So if the 6S was plugged in and I had the right wiring for the 6S, it would have metered it correctly. If the 9S would have been plugged in, it would have metered it correctly. But plugging the 6S into a 9S wired socket, instead of having what we would expect as far as the correct vectoring and correct phase relationships for the voltages and currents, we end up with one that looks like this. So that will be, like I say, next week. It's something that if you want to think about it, like I say, try to consider what might be happening there. You can, or just wait until next week and I'll take you through the process. It's not too painful. Like as you can see, in this, blue current stays right where it belongs. B stays right where it was, minus IB still, and then IC is just the voltages end up, that instead of having C to neutral voltage that has a relationship with this current, and well, C to neutral with IC and then C to neutral with minus IB, I have B to neutral with minus IB, and then I have A to neutral with minus IB, and then I have B to neutral with IC, and A to neutral with IA. And this vector will produce a stop meter. Like I say, even though there's plenty of load, plenty of current flowing through my meter, it's still going to end up being stopped. So it gives us something that we'll see next week. I don't want to dive into it too deep, but it'll give you something to think about yourselves even for the week. So any questions on that one for what I've shared with you today? Any questions on the 6 or 36, difference between them? Like I said, if you look in your Meterman's Handbook, there's a 46S and a 56S that are that Z-coil style meter. So I've never seen a 46S. I've seen the 36S. I've seen a 46S diagram from the Meterman's Handbook, but I don't have any of those diagrams myself because I just never have had any need to put those together. But if you look, you'll be able to see that in the Meterman's Handbook. So I think we're about done. It's just about 6. Again, any questions?
Good.
So I think we'll call it quits. Thanks for stopping by. Like I said, there's a couple of things. We have a YouTube channel that we'll be loading these up onto. The Metergod Mondays are going on onto YouTube, so you can see if you want to have a review of anything that I talked about. And then we also have a new Facebook page that is giving folks a chance to load up their work, their questions, their mishaps. It's becoming quite an active page, so if you're interested in either one of those, and you're trying to find out how to get there, let me know and we can help you do that. So with that, we'll call it quits. And all have a safe week, and we'll look forward to seeing you next week.